In this video, we're talking about when a function is differentiable, which is called differentiability, and when a function is continuous. And differentiability means when I'm actually able to take a derivative. So when I can find the slope of the tangent line at a particular point. Okay, so let's look at first when a function is not differentiable, meaning I cannot find an equation of a tangent line at a specific point. So one case is you can't if you have at that point, if the graph has a peak, or sometimes we call it a cusp, or there's a corner there. And if you think about what the slope of the tangent line is supposed to tell you, it's supposed to tell you kind of the direction and rate of change of a curve at a particular point in time, but you really can't do that for a point or a peak because that's exactly where it is changing. And so, I mean, would you say at A, would you say it's here or would you say it's here? So at a point, a peak or a corner, we say a function is not differentiable. The second case where it's not differentiable is if the tangent line at that point was vertical. Because what do we know about vertical lines? Well, vertical lines have an undefined slope. So that would be a second case where it would not be differentiable. And the last case is where it is discontinuous. And discontinuous means a break in the graph. So let me just draw a simple, like say we had some sort of line as the graph, but it was there was a hole at A. Well, we could not find the tangent line at a point because there is no y value at x equals A. So we would, because it's discontinuous there, we would say it's not differentiable there. So let's talk about what it means for a function to be continuous. A continuous function means you can draw the graph without ever having to lift your pencil. Without ever having to lift your pencil. In other words, there are no breaks or gaps. Okay, so clearly that would not be the case for this graph that we just drew above in number 3 because there's a hole there, so I'd have to skip over that hole and to continue on my line. All right, so let's talk a little bit more about continuity and being differentiable. So if a function is differentiable, then it has to be continuous. Okay, so that actually is a theorem. And so if it is continuous, then if it is differentiable, then it has to be continuous. It's not true the other way around because remember with the graphs on the previous page, something with a peak certainly is continuous. There's no breaks, but it's not differentiable because of that peak. We can't find an equation of the tangent line. But if it is differentiable, because to be differentiable, it has to be continuous, we know that it is continuous. So just a limit definition of continuity. So if you wanted to test out if a function is continuous, it would have to meet these 3 conditions. First of all, it has to be defined there. So it has to actually have a y value at x equals A. The limit has to exist, meaning the y value it approaches from both the left and the right have to be the same. And finally, the limit actually has to equal the y value of that function at x equals A. So let's use this definition in example 1 to determine whether the below graphs are continuous at 3. All right, so in other words, let's see which of these, if it fails to be continuous, which rule does it fail? So the problem with A is f of 3 definitely exists, it's equal to 4. And the limit exists. The limit actually is 2. From the left and right as x approaches 3, the y value is approaching 2 here. But the limit does not equal f of 3, so it fails rule 3. So it's not continuous because it's failing rule 3. Okay, how about the next one? Well, the function exists at 3. It happens to, the y value happens to be 2. That's where the closed-in circle is. But the problem is the limit doesn't exist because the limit from the left differs from the limit from the right. So it's not continuous, and that rule 2 is what it is failing. Well, C, it's not continuous because f of 3 doesn't even exist. It's going off towards infinity on either side of that, but there is no f of 3. So not continuous, that first rule, it's failing. And part D, again, it is not defined at 3. There's an open circle, there's a hole here. So it is not continuous. It's failing that rule number 1. Okay, so let's do a different type of problem here. Is f of x continuous at x equals 3? All right, so to figure this out, this is a piecewise function, and the graph is first going to be on, for x not equal to 3, the graph's going to be on this x squared minus x minus 6 over x minus 3, and you may be thinking, how in the heck am I supposed to graph that? Well, let's see, I'm betting we can, there's going to be a common term here, and we'll be able to cancel something out. So let's see, x minus 3, x plus 2 over x minus 3. Yeah, so the graph actually is the graph of x plus 2, except there's going to be a hole at 3. So if I graph this line of x plus 2, the y-intercept is 2. When x is 1, we're up at 3, and then there's a hole at x equals 3. So there'd be a hole at 3. And the y-coordinate of the hole would be 5. So 2, 3. So there'd be a hole here. Oops, open circle. Okay, well, so at the hole, the y-coordinate is 5. Well, let's see if that hole gets filled in. Well, it's at x equals 3, the y value, it says, is 4. Well, 4 certainly doesn't equal 5, so it is not continuous at x equals 3. And so you could say many things. The limit exists, but the limit is 5, whereas f of 3 is 4. So that's the issue there. Is it differentiable? Well, if it's not continuous, it's not differentiable. Okay, so that was one example. Let's look at another example that kind of talks about continuity. So here, determine the value of a that makes the function continuous. So in other words, what would a have to be for these two pieces to connect? Well, if I were to draw the bottom piece, I would plug in 0, and there'd be an open circle there, and the y value would be 1. So in order for it to be continuous, that open circle has to get filled in by the first function. So we want the first function, when I plug in 0, I want to get 1, the same as when I plug in 0 into the second function. So let's see what a would have to be. So 1 equals negative 2a. A would have to be negative 1/2. Then the two pieces would connect. All right, so this example 4, this is writing a piecewise function. So read the problem first and pause this and see if you can come up with a function here to describe this. Okay, so the cost, the easier piece is the cost, let x equal number of miles, as it says in the problem. So the cost for 0 to 200 miles is just going to be the cost per mile plus this fixed cost of 1,000 that the railroad charges. And so that's for miles 0 through 200. Well, after that, so when we're putting value greater than 200, so say we're going greater than 200 miles, I'm going to pay for the 0 to 200. So if I'm going greater than 200, I'm paying for the 200. So paying for the 200, let's see how much I'm paying there. If I'm paying for the 200, I'm paying $3,000. And then for everything over 200, I'm paying $8. So it's going to be 3,000 plus 8 x minus 200. I want to subtract because when I'm putting in values greater than 200, I'm only the values greater than 200 am I able to spend $8 per mile. I've already taken care of the 200 miles with the 3,000. Okay, and this simplifies, if you want to simplify it, this piece, it's 8x plus 1,400. All right, so the question is the function, we're going to determine if it's continuous and differentiable. So if we were to graph this, all right, so for 0 to 200, when I put in 0, I'm looking at the top line. When I put in 0, it's going to be 1,000. So I'll just write 1,000. And when I put in 200, we just said that's going to be 3,000. So something way up here. And then greater than 200, well, when I put 200 into 8x plus 1,400, I get 1,600 plus 1,400, which will connect. And then the slope isn't as steep, so something like this for that line. So it is continuous, but because we have a kind of a corner situation, it's not differentiable. Okay, so that is example 4. Let's do one more together here. And then you can work on the homework practice problems. All right, so let's get this next one. All right, so determine if the functions are continuous or differentiable. So the first one, if you're not sure what that looks like, you can put it in your calculator, but this function looks like, it's called the reciprocal function. It looks like this. And at 1, which is right around here, I've got no peaks or corners. It's continuous. So we would say it's continuous and differentiable at 1. If I were to graph, however, something like g of x, so from 0 to 1, I'm on x cubed. So 0 is 0, 1 is 1. I'd put an open circle there. But then when I put in 1 into the second, it gets filled in because 1 is still 1 on y equals x. And then let's plug in 2, would be 2. So the first graph is a curve, so it's kind of looking like this. And the second is a line. So it will be continuous, but it's not differentiable. Again, kind of a corner peak type thing. Okay, the last one, let's graph. It's going to be the line y equals x, except at 1. It's going to be a hole there. So there's a hole at 1. And at 1, the function actually equals 2. So this is definitely not continuous. And because it's not continuous, it's not differentiable at x equals 1. Okay, so that's a bit about continuity and being differentiable. So try the homework problems.